So here's my third lecture on torque and rotation from an AP Physics C class. Continuing my examples with using integration for moments of inertia of basic geometric shapes. So let's imagine we have a uniform sphere, some radius r with an axis to the center. That's going to be my primary axis for integration. And we're going to divide that sphere up into thin disks of some thickness dx, whose moment of inertia is known from the previous example. Remember, if I just let the cylinder get thinner and thinner, or shorter and shorter, it could end up having a very small thickness dx, and the moment is still 1/2 of the mass times the radius of that disk squared. Now the radius of the disk. So the center of the sphere is not shown with a dot, but the distance, capital R, extends from the center of the sphere out to the surface of the sphere, and then I'm some distance x along the axis from the center of the sphere. So the radius is going to be the difference of squares, r squared minus x squared, square root of that. Now the volume. Well, it's very thin, but it's going to be pi r squared, the surface area, times that thickness, which I can replace r squared with capital R squared minus x squared. And the mass is just, rho times that volume. And so there we have my integrating variable dm in terms of dx. Now, one of the problems, though, is as I integrate along this axis, this radius varies. And I don't have a way of incorporating that into this expression, the way it's stated right now. I've got integration is integral of r squared dm, but r varies, and I've got to have it varied in terms of x. So let's go back to that previous example. We had a moment of inertia, 1/2 mr squared. If I take a derivative of it, I've got di is equal to 1/2 r squared dm. So now I can go back and I've got r here, and I've got to figure out how to incorporate it. Now this differential form works because I haven't lost the ability to use x as the integrating variable, because you can see dm is in terms of x. So if I let the thickness of the cylinder drop down to dx thickness, I can still use x as my integrating variable. So this works. So let's just replace r with what it's equal to, which is the square root of r squared minus x squared, but now it's squared. And so my differential moment of inertia is going to be 1/2 of r times r squared. So I've got r squared in here. I'm going to integrate from 0 to r, and I can do that for just 1/2 of the total sphere and multiply that by 2. So here it is times 2. What I had up here times 2. And here, if I just simply expand this into r to the 4th, x to the 4th, and 2r squared x squared. When I integrate, you can get some terms. I'm not going to go through it, but you end up with this expression here when you collect all the terms. I've got here r to the 5th, because I end up with x to the 4th, and antidifferentiation of that is 1/5 x to the 5th. So I end up with r to the 5th. Now, again, it's more convenient typically, unless you know the density, to convert it back into an expression that has the total mass of the object, because we can weigh that, typically weigh it, and we know the mass. We don't necessarily know the density. So if I divide this term out by this term and then multiply it by m, I end up with 8 goes into 4 twice, and 15 goes into 3 5 times. So I end up with 2/5 mr squared, r to the 5th divided by r cubed. So there it is. That's the moment of inertia of a sphere, no matter what axis I pick, obviously, because a sphere it's got that symmetry. Well, let's look at a different method. So we did the disk method. There is another method that we could use that's fairly commonly applied, and that's the shell method. And I did that when I did the cylinder. So let's go back and try the shell method. Okay? So here I've got some little thickness dr for the shell, and the radius of the shell is a function of how far away I am from the center of the sphere. So distance x away, the greater x is, the smaller r is. Now if I look at, again, just doing 1/2, integrating over 1/2 of the sphere, just from x equals 0 out to r, the volume is going to be the circumference of the shell times its thickness times this distance x from the center of the sphere. That's dv. Mass, all right, so it's going to be, I've got to incorporate rho in here, don't I? So the total mass, if I include both halves, I can go all the way from here to here, just multiply by 2, even though I'm integrating over this 1/2, right? So there it is. Now, again, r squared is equal to the radius squared of the sphere minus this distance x along the x-axis from the center. I've got to get my differentiation in terms of x. So the way this is written, I've got r dr is equal to negative x dx. And that's just because the x and r are inversely related, aren't they? The farther I go out along the x-axis here, the smaller r is. Okay, just the same thing as before now. The amount of mass is going to be volume times rho, but now I've got this negative term because I've written it in terms of x, haven't I? I've replaced r dr with negative x dx. So I've got negative x dx times x, or I've got x right here times x, is negative 4 pi rho x squared dx. Remember, this is just a differential expression. The negative sign just because the cylindrical shell decreases in size with increasing values of x along the x-axis. The moment of inertia then would just be r squared times that, so I end up with r squared in here, and I'm using the same trick as I did before. I can replace r squared with big R squared minus x squared, and there's my integral. Now I've got this negative sign, and it's still here because I'm still thinking about r. R increases from 0 to r as x decreases from r to 0. I mean, they're inversely related, aren't they? So I can just reverse signs. So I want to integrate as x gets larger. X goes from 0 to r as the radius goes from 0 to r. Or rather, what I mean is, originally it was defined as with respect to r. R goes from 0 to r, but x goes from big R to 0, and I just reversed it so I can have x go from 0 to r. Okay, so I reversed the signs. Anyway, again, I've got to the 5th power here, don't I? And I get the same expression as before, same answers as before, same process. Divide out by this term, divide these two terms out and multiply by m, and I end up with the same answer, of course. That's good, right? It's a good thing. Okay.